Hey everybody, so here's another problem. And so for this problem, we're going to calculate the pH from Ka. And so we have an acetic acid solution, and that acetic acid solution is 0.3 molar. Now it seems like we're not given a lot of information, but I will say that we do have the Ka. So if we have the Ka, that means that we should be able to find the equilibrium conditions. Once we have the equilibrium conditions, we can probably calculate the pH, or at least we hope that we can. So let's take a minute, and I'm going to set up this on my little notepad, and we'll give it a shot. So I think that there's value in showing you how to set up a problem like this. Okay, and so we were given acetic acid. Helps if I actually have a pen. So HC2, C2H3O2. Let me see if I can get that to write a little bit better. Okay, so I'll do it down here. Okay, so C2H3O2 plus H2O, and this is aqueous, this is a liquid, is in equilibrium with H3O plus C2H3O2 minus. Okay, so this is our equilibrium reaction. Okay, the acid and base reaction never change. They're always the same. The acid plus water gives us the hydronium ion plus the ion of the acid. Okay, now in order to solve this, we have to set up an ICE chart. So let's set up an ICE chart. Okay. And I think it's beneficial that in your head to try to figure out where in the ICE chart you're trying to go. Okay. Now, the question asked for the pH. Okay. So that means that we need to get the equilibrium concentration of hydronium ion and then calculate the pH. We were given that the Ka equals 1.8 times 10 to the minus 5. Okay, and we were also given that the initial concentration is 0.3. Okay, so let's get into this problem. Now, you're more than welcome to pause the video and see if you can work through the problem and see if you can get to certain points and see what you can get to. Okay, so let's keep in mind that water isn't going to play a role in the equilibrium. Okay, so I'm gonna cross it off. Now, how much hydronium ion do we have to start with? 0. If it's not said in the problem, we assume 0. And how much acetate ion do we have? 0. Okay, so now let's do the equilibrium. Okay, again, this is going to shift to the product side. Anytime there's a 0, we always shift towards the side with the 0. So this is going to be minus x plus x plus x. Okay, and so this is 0.3 minus x. This is going to be x. This is going to be x. So are we there? Not quite yet, but we want to use Ka to solve this problem. So it's going to be the concentration of H3O plus the concentration of C2H3O2 minus all over concentration of HC2H3O2. Now, we don't have numbers for those equilibrium constants, or those equilibrium conditions, but we do have things to put in. We have values to put in. So for Ka, it's 1.8 times 10 to the minus 5, that was given in the problem, equals x times x all over 0.3 minus x. Now, to solve this problem, again, I think it would be beneficial for us to show the calculator here. Now, to solve this problem, I am going to assume, assume 5%. So the assumption of 5% is that this value of x here is going to be so small that 0.3 minus anything very small is still going to give us around 0.3. Okay, so that means that when we solve this, we can get rid of this x, and that saves us from having to do the quadratic equation. Now, you're more than welcome to do the quadratic equation, but as a chemist, sometimes doing that math is unnecessarily precise, okay? So now let's solve it. So we get 1.8 times 10 to the negative fifth times, again this is on the bottom, times 0.3 equals x squared. Okay, so let's do that. 1.8 times 10 to the, notice how I'm writing that in my calculator, times 10 to the negative 5 times 0.3, and so we get 5.4 times 10 to the minus 6 equals x squared. And now to solve for x, we take the square root. So I do second square root of 5.4 times 10 to the minus 6. Okay. So when I take the square root, we get a concentration of 0, or we get x equals 0.0023. Okay? Now, that x is equal to, if we look up here, is equal to the concentration of H3O plus and the concentration of the acetate ion, C2H3O2 minus. It is not equal to this equilibrium concentration, but we can figure that out. I understand that the problem, when we go back and look at it, is really just trying to determine the pH, but just know that we can figure out this equilibrium, we can figure out this, we can figure out this, we can figure out this. Okay, so let's continue with this. So that x equals the concentration of H3O plus, and it also equals the concentration of C2H3O2 minus. Okay. Now, we're not done because the question asked for the pH. pH equals the negative log of the concentration of H3O plus. Well, do we have the concentration of H3O plus? Absolutely. So that equals the negative log of 0.0023. Okay, so again, let's plug this in. Negative log of 0.0023. And when we do that, we get a pH of 2.64. Okay, so that's our pH. Okay. So what this does is this reinforces the idea that there's really only two types of equilibrium problems, regardless if it's acid or base or whatever. It's always trying to find the conditions or trying to find the constant. So if we're given the constant like we were in this one, we should try to find the conditions. Yes, we have to take it a step further and find and then find the pH. But the pH is related to the conditions. Okay, so I hope this makes sense, and have a great day.